Okay, so today what I want to talk to a little bit about is the closed system energy balance. So let's say for a moment that we have what we'll call our system, right? And everything external to the system is going to be the surroundings, right? And let's say that this system here has a total internal energy that we'll designate as U sub I, or U initial. Now, I can do a number of things to this system, right? I can add energy in the form of heat, Q, right? I can withdraw energy, right, in the form of heat, Q, right? And this would be a negative flow out. And this is what we would consider a positive flow in, right? The system could do work on the surroundings, right? So I could expand this boundary, say, like this, right? And the system will do work or lose energy, right? Because it will expend energy doing work on the surroundings. So this would be, right, work negative done by the system. Alternatively, right, the surroundings could do work on the system, right? Change the system boundary, deform the system boundary in this way, right? And this would be doing work on the system, right? So this would be work with a positive sign going into the system. So I can add heat or work to the system, and I can add, I can add or subtract heat from the system. I can add or subtract work from the system. And that's pretty much all that can happen, right? Because this system is, right, this system is closed, right? No mass crosses the boundary. So I could do all of this, and at the end, right, I would have a final internal energy, which I'll denote as U final. So if I take the difference between those two states, right, the final internal energy of the system after I've added or subtracted all of the energy through heat or work that I want, I can write that, I can write U final minus U initial, which we'll say is delta U, is equal to all of the heat that I added over the entire thing, right, or removed, plus all of the work that I added or removed from the system, right? So this is important, right, because we see that I could manipulate this system in a variety of different ways, but it could end up looking the same as it did at the beginning, in which case the overall change in internal energy could be zero, but I still would have added or subtracted a great deal of energy in the form of heat or work, right? So that brings us to a discussion of two things, right? One is which is the state function, right? Of which internal energy or delta U is, right? It depends only on the initial and final conditions, right? So I could take this system, I could manipulate it all I want, I could do anything I want to it, I could add a whole bunch of energy, I could subtract a whole bunch of energy, I could do a whole bunch of work on it, I could extract a whole bunch of work from it. But if I ended up at the same state as it was at the beginning, then the total change in internal energy would be zero, right? But I could do that a variety of different ways via different amounts of Q and W. So Q and W in this case, right, and Q and W in all cases are what we refer to as path functions, right? And they depend on the specific path path or route I take to get to the changes. So to give you an idea of how that works, right, let's say that this represents, right, U initial. And over here, right, U final happens to be the same state, right? So these two are equivalent. So delta U between those two states would be 0, right? But in order to get between them, right, I could add a little bit of heat and subtract a little bit of heat and do a little bit of work and remove a little bit of work, right? So this is Q plus W for path 1, right? A different path that I might look at or I might choose might go the opposite way. It might do a bunch of work, remove something, come back, right, do that, and end up here, right? So I have ended up at the same state between initial and final conditions, but I've taken a different path to get there, right? And so this would be Q plus W for path 2. And so there would be an infinite number of different ways that I could combine those two things to get between those two states. So state functions are very important in thermodynamics and in engineering because they only depend upon the final or initial state of the system, which is often defined by variables that we control, like temperature, pressure, flow rate, things like that. Path functions, on the other hand, like Q and W, heat and work, are dependent upon the amounts that I do. And I can do different amounts and reach the same states. So state functions and path functions. So this is really what we want to emphasize, right, for this, is that the open system, or I'm sorry, the closed system energy balance, right, for a system is that the internal energy of that system, right, changes in the internal energy of that system are dictated solely by changes in heat that I add or remove for the system and work done on or by the system.